So up next is Kyle Gwinnup. He's a senior researcher with CarbonBlack, and he's going to talk about some cool stuff on analyzing binaries with AWS serverless architectures.
Thank you. Let's make this a little taller. Okay, so can you hear me all right? Is this good? All right. So yeah, like Rob said, this is going to be a talk on serverless architecture and binary analysis. I like to frame it as more of, there's a design pattern, like a system level design pattern. I like to frame it more as this is a system level design pattern, and the concrete example we're using is binary analysis. It happens to also be serverless, which has a lot of nice properties for us, being more interested in the data and less interested in managing servers. So this talk is going to go through three phases. The first one is outlining the actual architecture and how data flows through the system. The second one is going to be on how we do the binary analysis and how we think about the feature extraction, and when we, as program analysis, training, how we actually think about the features and how we do the extraction. And then the third example is this was not a perfect system. There's some things I wish we did differently. But fortunately, it is actually easy to change because we're not managing a whole lot of stuff. It's just interacting with APIs. And this talk does heavily rely on AWS. However, you could probably get similar results with whatever your cloud provider is. So yeah, serverless architecture design. So the idea with the layout here, the flow chart, is to make this thing, make the whole system as simple as possible. We don't want to have to debug a bunch of complex problems, particularly when you're doing these parallel systems at scale. So information flows in this diagram from left to right. There is kind of the input to the system. There's a controller, which does a lot of the pre-processing and filtering of data, and then kind of routes it to where it needs to go. And then there's the kind of the backend and the main system that does the processing. So key component is obviously queues. The workers are in red there, and then the data storage. But as you can see, we have two inputs. What awesome system would be awesome without a web interface, and then we also have a Python API, which is typically what we use. So start at the beginning of the system, or the core of the system is this AWS Lambda. And this is really the hub, of a hub and spoke model. This is the hub. All information would flow directly through this, and ideally it flows through here for a number of reasons. One, it's easy to debug, or easier to debug than like a larger system. Two, kind of just this thing can live inside of our VPC. So as we route traffic in and out of our system, we do both static analysis and dynamic analysis. And our dynamic analysis actually doesn't live in AWS due to AWS policies. So we have to route traffic into our internal system, which is a host of ESX. So this is really nice because the Lambdas can live in that system. The other thing that's really cool about this is because this is just the main entry point, it's much easier to document the entire system. Like this is all you need to document. This is the entry point for any type of interaction with the system. And then, of course, it scales, which is really nice. And then in building the system, in building AWS Lambda, it encourages a functional programming style of writing the system, because a Lambda is essentially a function, and the function just takes some input and it returns some output. And this is very easy to test. So how do you interact with the Lambdas? Well, AWS also offers a service called Gateway, and this is essentially a glorified, scalable Nginx server, or Apache server, that routes all the traffic into the system. And it's really cool because you can route traffic into the AWS Lambdas, or you can also route traffic directly to S3. So if we're uploading or downloading binaries, this is typically how we would route traffic. Additionally, this combination of Gateway, Lambda, and S3, and then optionally any type of database store you have, you can serve up an entire serverless website. You don't have to do any maintenance of any Flask app or anything on the back end. You can just upload your files, your JSON bundle, and your HTML to S3, and you can just point the gateway to the S3 bundle when you hit that URI. It is a little bit tedious in some aspects. It's actually very simple in all aspects. The most complicated part is the S3 interaction, and that's just kind of defining the routes and like where you are in the bucket, and like where it would concatenate the URL of the URL that's coming into Gateway to the actual bucket where the file sits in the bucket. But that's actually pretty simple. It's as complicated as it gets. But the benefit of all of this, actually, when you define the whole thing and you go through the tediousness of building the gateway and defining all the URIs, the query strings, the post parameters, you get really awesome Swagger documentation for free. And this is great for giving to new employees or anyone else who's going to be using the system. So the data model. This is one of the most exciting parts. Is at least for me, was Postgres introducing a JSON B data type. So when doing binary analysis, we really have two types of data. We have like files, binaries, and larger non-primitive data types. So if you dump the output of strings, that's something we're not going to want to store in Postgres. We'll put that in S3. But like your primitive data, we all put in JSON. So these are your integers, your floats, your strings, lists of strings, and then primitive object types. So those all get put into JSON, and JSON B within Postgres is decomposed into binary format on the Postgres backend, which allows you to do very efficient queries. For programming analysis needs, we tried several different approaches. We used like S3 only with Athena and other things. But Postgres, for what we were doing it, or for how we're doing this, and for where we see this going, it's going to scale quite well. So those are the two interactions. But the Postgres holds the metadata, and then the metadata would point to either the primitive data type or into the S3 bucket, wherever that file would live, for each binary, or each sample. So what does a sample look like in the JSON metadata store? Is going to look similar to this. This is a made-up one just because there are actually a lot of data with the amount of features we're extracting, but this is a very simple one. So this shows pretty much entirely primitive data, except for one point, which is towards the bottom we have strings raw. So this is going to be an output and just simple pointer into S3. So now when we query this, if we do have to do any like post-processing data of like of the feature that's stored in S3, we can just grab that S3. Typically, we don't do that. When we're doing our model, we're looking for primitive values, for something that we can dump into an Excel spreadsheet or into a Python notebook or pandas or something. So this is more or less what we're looking at. Additionally, at the bottom, we also do dynamic analysis. You can use dynamic analysis with this exact same system. You just can't do it on AWS. You need to stand up your own infrastructure. I just put this on here because every time I use Postgres JSON B data type, I'm impressed. It's really standing on the shoulders of giants. So this is an example of just how we do like one particular query. Looking at the data, you can dig into the JSON structure itself instead of like, if you've ever done with like NoSQL, like document stores, it's a little bit more complicated and it's actually less efficient. But with JSON B, this is actually incredibly efficient. So we can dig deep into the JSON, pull out the exact features that we want. So disregard the top part, which is kind of the table stuff, but down at the bottom you can actually see it's digging into the JSON and it's returning the actual values that you would want out of the field. And this, of course, since it's SQL, it's going to return into a nice SQL table that we can just export into any type of pre-model that we're going to do. The other really nice thing is, because it is SQL, any analyst we bring on board, almost everybody knows SQL, so they're going to jump right in here and be able to do the job that they need to do. Okay, so now the binary analysis. So this is the part that I think can change. So we've outlined the system and how data goes through. It goes through like AWS Lambda, it goes back and hits a bunch of queues. The workers will pop messages off. These are the workers. So this is the part that you can change the analysis. So the concrete example is binary analysis here, but you can change this to do whatever type of feature extraction you're looking for. Again, this is another simple flow chart. This is of the analysis worker. And we have a concept which, I don't know, so our modules, our analysis modules, just operate in one like Python file. So the analysis worker will pop a message off the queue, in this case, and that message will contain, among other things, a hash, so the file that we're interested in doing analysis on, and this file can be PE, ELF, Word doc, and URL in some cases, it would point to a URL. And then it'll also contain a list of analysis modules. So these are the actual features we want to extract from that binary. So it pops that message off the queue, downloads the binary or whatever it's looking for from S3, puts it into its working environment, and then it serially goes through every list of analysis modules and extracts those features, and then continues to the next one. And again, this thing goes back through the controller. So all the interaction goes back through there except for the S3 stuff. But all the interaction goes back through the controller so you can debug it and you can actually see what your workers are doing a little bit clearer. So how do these workers live? How do they fire up? Prior to the system, we had we'd spin up a bunch of EC2 instances. We had a bunch of scripts to make sure all the analysis modules were pushed out to the new EC2 instances, and everything was right there. But now we're using, and that was also running Docker on the EC2, but we still had to push things out, and it was kind of a pain. So now we're still using Docker, but now we're using the service that AWS recently introduced, which is AWS Fargate. And Fargate essentially removes the EC2 component, and now you can literally just build your Docker container, upload it to AWS's Docker, their ECR, I believe is what it's called, and then just hit play, and it'll start that Docker container, and it just runs. And it's super cool, particularly for like programming analysis, because a lot of the work we do requires like not necessarily long-running tasks, but tasks that can't necessarily run in Lambda. So we make heavy use of Radari, which is an open source reverse engineering framework or disassembler, and that runs great on in this system. So I did mention this was serverless. I sort of lied. There is actually one server in the loop. That one server is our Jenkins box, which, among other things, does the testing, deploying, and all that stuff. But it also monitors the queues. So we have several queues for dynamic analysis and the static analysis and various types of static analysis we're doing. So it monitors those queues, and it'll spin up the workers based on an algorithm we have, so we don't have too many workers running at one time. This is due mostly to cost. You could have it. There's ways to fire up the workers for each message that's on the queue, but we were balancing cost and stuff. So we end up having one server do that. So when that goes down, actually the whole system kind of goes down. Except for the data stuff. The data's still there. So I did talk about analysis modules a little bit. This is how we think about the features. So we think about the features as a pure function. Pure is as much as you can think about purity in an impure world. But every analysis module, like I said, is one feature. So one feature would be like the file size. One feature would be the imports, or one feature would be the complexity score, or whatever it is. So we just want to focus on just that one thing. So the idea behind that is to make it simple, and it codifies the definition of that feature. So this is useful when you're reading different papers and they define a feature in a certain way, and now you can codify that exact feature in the way that they defined it and use it in your model to verify the result. It's also useful when you're sharing among other researchers, and then you want to figure out how did they calculate complexity score, for example. And then you can look right in this Python module. It's very short. It only does one thing, and you can easily see that. So in our goal to make this as simple as possible, but no simpler, the analysis modules require really the knowledge of only 3 functions. So the whole thing is Python, but the first function is actually just a decorator. So analysis module only contains one function. The interface or the contract with the whole system is that Python file contains one function, and its name is returns. It could be anything, but we called it returns. And it is decorated with this cache returns. So the cache returns simply means that that function will only run on this binary or on this file if it hasn't been run before. So if you run strings on one file and another module needs to use the output of strings, you don't want to rerun strings every time, right? So cache returns caches the value of that and then stores that for any other module that would need it. The other 2 are saving the data. So this is just a nice kind of friendly wrapper around how we store the data, and I'll talk about these a little bit. But one saves the data directly to the metadata store, which is JSON. And the other saves the file or whatever you're saving to S3 and then puts the link inside of the metadata store. So this is an example of a blank analysis module. So this is all you have to do to get a module started. So there's some boilerplate up top, and then the meta field is more or less just for the front end to display to whoever's using it if they want to launch a particular analysis and they want to pick which modules they're using and they get a description of that. But at the bottom, we're implementing cache returns and then the single function. Now this function returns takes the sample, which in most cases it's the hash, and then it uses the backend to figure out how to download the hash. And then the environment, which is just, in this case, in all cases, it's just the message that's popped off the queue, but it's actually useful for there's some creative things that you can do when you have really long-running tasks or tasks that need to wait. Like if you're submitting data to something and you need to wait like an hour, there's counters in there that you can increment and push messages back onto the queue and then pop those off. We have very few of those use cases. But again, because this is we're trying to maintain the functional programming paradigm, every function needs to return a value, and these values can be used with other modules. So let's look at a concrete example. So this, again, there's boilerplate up top. This one actually imports the strings module. So the first line within the function, it actually calls, I don't know if you guys can probably see it, but it calls the strings returns function. So like I said, this is cache. So if we have multiple modules that need that strings return, this is only going to run strings once just to save time. And then what this does is just returns the output of that, does some stuff to it, some mutations, and then basically searches for that binary, searches for different keywords within there, and then just counts them. This is a very simple module. And then at the bottom, towards the bottom, there's the save data. So this is probably the more interesting piece. And the really, really scary part about Python, but also what makes it really awesome, is we can pass really any type of data into a function, which is I guess it's awesome. In this case, it is pretty cool. If you have the back end that handles all the cases. But the list here defines the keys and the subkeys of how the data is stored. So for example, if we had an empty JSON blob, this would save the value of ret into the root key, subkey, then that subkey is going to contain an object, which is going to have a key called subkey underneath, or substrings, then an object that's going to have subkey, which is going to contain the actual JSON blob here, if that kind of makes sense. And then again, this returns ret because then, or returns the value, because then other modules may want to use this. Okay, so you have this system, you can ingest all this data, we do a lot of program analysis, we write all these modules. What does it all mean? So the core thing is that we can quickly go from feature, like an idea, when we're doing our analysis, we can go from an idea to an implementation and then put that against all of our files in the corpus very quickly. The main thing is we also get easy access to the data, given JSON-V's data store, and we manage mostly zero servers for all of this. The other really cool part is there's a lot of papers out there that are doing like malware versus non-malware, and we can basically take those papers, given the hashes, given their features that they're extracting, and then their methods, we can ingest all the hashes really easily, we can define analysis modules based on their features, and then we can reproduce the results or validate their results, which is really cool. The other really cool part of that is we already have a corpus, and since we're building these modules, we can automatically run them against everything in the corpus, and we can validate their results against previously unseen samples, unseen to them. So lessons learned, the big one is we use Docker for all of our things for most, but I would say 60% of our analysis modules could probably be done with AWS Lambda. We do have the requirements of like Radari and some other like tools that can only run in Docker, but if I were to build this again, I would probably have another queue for pushing things to Lambda and pushing things onto the Fargate instance. And then the other thing, gateway, it's like a little bit of latency, just because probably it has to live in a VPC, so get an IP address and all these other things every time. So what is our goal? Our end goal is obviously, I think, or not, maybe not obviously, is we really would like to say this is malware, this is not malware, like this is hot dog or not hot dog. But that's a large task, and there's a lot of nuance to that, and it's a very difficult problem. So what we're actually doing is we're kind of working our way there, and we have little stepping stones. In each stepping stone, we add value to the company, and one of the pieces of value that we add is for our analysts, we actually limit the amount of time that they're working on doing reversing tasks. So just a quick example, since I'm running out of time. Frequently, we get dropped with 20 samples of malware. Hey, this malware family A. Tell us about it. So before we had any kind of system, you'd spin up IDA or whatever your reversing platform is, and you just start chugging through them all. So now with the system, we can actually throw them all into our analysis engine, run all the modules against it, and then query using Python Notebook or whatever, query that data, spit out some graphs. And for this example, I can't remember what the APT or whatever the malware family was, but we can clearly see that there's 3 types of examples here, polymorphic in probably 3 cases. And then going further with some of the features that we've extracted, we can actually do a clustering. So this is an example of just the principal components for clustering on only the functions, so the imports. And again, we can see they're tight clusters. So what this does is it helps us frame our analysis, or it helps the analyst frame where they're going to look. So now we can just diff maybe these binaries and then only analyze one of them in depth. And it just helps them kind of think about the problem a little bit differently. So with that said, are there any questions?
All right, so this works. So there was one thing I was curious about. As you mentioned, AWS, especially Lambda, has some resource constraints for execution. Have you run into any malware that tries to exhaust those resources as an anti-analysis technique?
Not yet, but there's definitely Lambda is limited to 5 minutes and then a certain amount of memory. We haven't run into that case yet. Most of the analysis we do is static. We do run into that in some of the dynamic analysis cases, though. But that's not with Lambda. But yeah, good question.
Do you have to all right, test? All right. Do you have to integrate new data streams or new types of data stores, or do you have fairly set places where data is coming into the system and then a static place
Yeah, I think I understand your question. So, what? Yeah, so I think he's asking, do we have like flexibility in how we store data both on the input and the output, or like where it goes? Yeah. So as far as the output, it's pretty static to this, but the input we do have various scripts that also run in like cron jobs that ingest data from various sources and do some processing and then shove it through the system. But the backend, yeah, it's pretty static on that. Actually, sort of. So at one point we were running Athena, just dumping everything, the JSON into S3 and then running Athena on top of it. But then we switched on the back end. But the cool thing about the system with storing the JSON is we can literally just flip 2 functions, and then now we're using Postgres instead of S3. So at least the back end is a little bit flexible, but it's, yeah. All right, thank you.
Another question?
Yeah. I want to ask if your setup, is it allow for one analysis module to depend on another?
Yes, yeah.
So how you get around to that? I don't quite understand from your diagram.
Oh, okay, so every function has the single interface, there's just another function, and that has the decorator, which then behind the scenes it caches the value of that function. So if another module imports that module and it calls that function, it checks the cached value first, and if that value exists, then it uses that instead of rerunning the whole module. Does that make? All right, thank you.